Imagine pulling into a mechanic shop, right? And you just hand over, I don't know, more than $1,100 to replace your car's tires after just 30,000 miles.
Ouch. Yeah, that hurts.
Right. Or finding out you need to pay $100 for this super specialized service to maintain a set of brakes that you almost never actually use.
Yeah, that's the reality a lot of people are waking up to.
Exactly. So if you are listening to this thinking, wait a minute, the whole point of an electric vehicle was to eliminate those annoying maintenance costs, you are definitely not alone. Okay, let's unpack this. We are about to shortcut your way to being fully informed on a topic that has, frankly, a lot of mythology swirling around it.
Oh, definitely. So much mythology.
Yeah, so our mission today is to figure out what really goes into owning, driving, and, maintaining an electric vehicle.
Because we have finally moved past that early adopter phase, millions of people are driving these cars every single day. And the reality of living with these complex machines is it's really starting to crystallize sometimes in ways the marketing brochures conveniently gloss over.
Right, they kind of leave out the fine print.
Mhm.
So to get to the bottom of this, we have pulled together a stack of sources that look at this from every possible angle. We are diving into a very comprehensive EV maintenance guide from the folks at Car and Driver. We're also looking at some highly practical cold weather survival strategies from Athlon.
Which is crucial data, by the way.
Super crucial. And finally, we're analyzing an incredibly detailed expert guide on prepping your EV for long-term storage. Today, we're taking you on a journey into the hidden life of your electric vehicle.
I like that, the hidden life.
Right. We will start in the freezing trenches of a daily winter commute, move through the invisible physics that are tearing up your tires,
Yeah.
and end up exploring the really delicate psychology of putting a 4,000-pound computer into hibernation.
I really appreciate that framing. There is this completely pervasive myth out there that because electric vehicles lack the hundreds of moving parts found in a traditional gas engine.
Like no pistons, no spark plugs.
Exactly. No timing belts. Because they don't have those, people think they're somehow entirely maintenance-free. We just need to bust that myth right out of the gate.
Consider it busted.
They are not maintenance-free at all. The maintenance is just, fundamentally different.
So let's start with the most immediate, really visceral challenge an EV driver faces, which brings us to our first stop on this journey. Temperature. Specifically, the freezing cold.
The enemy of the battery.
Totally. According to the Athlon data, when the temperature drops down near freezing, you can actually see a massive 30 to 40% drop in your driving range.
Wow.
Yeah. Like if you have a car rated for 300 miles, suddenly you're looking at barely cracking 180.
And that changes the entire calculus of a daily commute or, a road trip. The sources explain that an EV battery operates most efficiently in a very, very specific thermal window.
What's a window?
It's between 20 and 25 degrees Celsius. So for those of us using Fahrenheit, that's roughly 68 to 77 degrees. Essentially, your car's battery just wants to live at room temperature.
Okay, reading through this made me think of an analogy. An EV battery is basically like a human body.
Oh, how so?
Well, it absolutely hates getting out of a warm bed into the freezing cold. And if you force it to, it has to burn a massive amount of its own energy just to shiver and warm itself up, to a functional baseline before it can even think about doing any actual work.
What's fascinating here is the actual physics behind your shivering analogy.
Right.
The battery isn't literally shivering, of course. But in a cold lithium-ion battery, the internal electrical resistance becomes much, much higher.
Which means what, practically?
It means the electrochemical reactions that allow the battery to release its stored energy become incredibly sluggish. So to combat this, the car has to power a dedicated resistive heater, or a heat pump, to physically warm the liquid coolant surrounding the battery cells.
Wait, so it's using its own battery to heat the battery?
Exactly. You are tapping into your battery's stored juice just to create an environment where the battery can safely release the rest of its juice. That internal resistance is why you basically bleed so much energy before the wheels even turn.
Man, that's wild. Well, Athlon offers some really specific workarounds for this cold weather drain. The biggest strategy they recommend is to preheat your car while it is still plugged into grid power at home.
which is incredibly smart.
Right. Let the electrical grid do all the heavy lifting of warming up the battery's coolant and the air in the cabin, rather than draining your battery's reserves before you even pull out of your driveway.
The contrast with internal combustion engines is striking here, actually. Gas engines are, honestly, incredibly inefficient.
Oh yeah, they waste a ton of energy.
Right, they waste about 80% of their energy simply generating heat. But in the winter, that wasted heat is routed into the cabin to keep you warm.
Right, it's like a free heater.
Exactly. But electric motors are highly efficient and barely produce any residual heat. So without a roaring fire under the hood, the car has to basically manufacture that heat from scratch.
And that leads me to a piece of advice from the sources that I really have to push back on.
Oh, what's that?
Well, they suggest prioritizing your seat heaters and your steering wheel heater over the general cabin climate control. They recommend putting the car in eco mode, which deliberately limits the heating intensity of the main vents.
Right, yes.
Now, if I am severely limiting the cabin heat and relying only on my seat heater, am I just supposed to sit there freezing my face off for the sake of a few extra miles of range? I mean, come on.
I get that. People often interpret eco mode as like a punishment setting, but it's actually a fascinating lesson in thermodynamics.
Okay, hit me with the science.
Heating the air inside a large, poorly insulated glass and metal box that's moving at 60 miles an hour through a freezing environment, it takes an astronomical amount of electricity. Air is just a terrible thermal conductor.
That makes sense, yeah.
However, heating the driver directly through the seat and the steering wheel relies on direct physical conduction. It takes a tiny fraction of the electricity to heat solid objects that are actually touching your body than it does to heat the constantly circulating air all around you. So eco mode shifts the energy burden from heating the empty space to heating the human core.
Okay. I guess I can wear a beanie. So the car is fighting high internal resistance in the battery, and it's fighting to keep the cabin warm. But it's not just the battery struggling in the cold.
No, the physical tires are fighting a battle too.
Exactly. The sources point out that cold air contracts, meaning tires lose roughly 0.1 bar of pressure for every 10 degrees Celsius drop in temperature. I have to ask, what does 0.1 bar actually mean to me when I am looking at my dashboard tire pressure gauge?
Good question. 1 bar is roughly 14.5 psi, or pounds per square inch.
Okay.
So a 0.1 bar drop is about 1.5 psi. If the temperature drops 30 or 40 degrees Fahrenheit overnight, your tires might lose 4 to 6 psi.
Wait, really? That seems like a pretty decent chunk of air to lose overnight.
It is. And it significantly increases rolling resistance. You are basically driving on slightly squishy tires.
Squishy tires do not sound efficient.
They aren't. A deflated tire has a larger contact patch with the road, which creates more friction. That demands more power from the motors just to push the car forward.
Add to that the fact that air resistance increases exponentially with speed. Athlon notes that dropping your cruising speed from 120 kilometers an hour down to 100 makes a massive difference in cold weather.
Oh, absolutely.
Because the cold air is denser, you are literally fighting to push a heavy vehicle through thicker air.
Right. Daily winter driving requires the vehicle to wage a multi-front war against the elements. It's fighting internal battery resistance, increased aerodynamic drag from the dense air, and increased rolling resistance from deflated tires.
Which is just exhausting for the car. All that extra energy required to push a cold battery and squishy tires forward brings us to the actual physical toll on the car itself. Here's where it gets really interesting.
Let's hear it.
If the daily commute is a constant battle against friction and gravity, what is that physical struggle doing to the rest of the vehicle? People buy these cars expecting to save a fortune on gas and oil changes, but they might be blowing all those savings on rapid tire wear and completely unexpected maintenance fees.
Yeah, this is exactly where the zero maintenance myth completely unravels. Electric vehicles are significantly heavier than their gas-powered counterparts.
Oh yeah, because of the batteries.
Exactly. We are talking thousands of pounds of dense battery packs spanning the entire floorboard.
Car and Driver share this shocking statistic from their long-term test of a Tesla Model 3. They had to replace their Michelin Primacy tires at just 30,000 miles.
30,000, wow.
Yep. And the cost for that replacement was a whopping $1,157.
30,000 miles is remarkably quick for a modern set of tires to degrade, but that sheer weight constantly grinds the tread down.
Right.
And it is compounded by the instant torque that electric motors deliver. When you press the accelerator on an EV, there is no engine to rev up the power, goes to the wheels instantly.
Like a rocket ship.
Exactly. So every time you accelerate quickly from a stoplight, you're putting immense sheer force on that rubber. It just chews it up.
It totally makes sense that the heavy weight destroys the tires. But what about stopping all that weight? Let's talk about the braking system.
Oh, this is a great topic.
Electric vehicles use regenerative braking to slow down. Can you explain the actual mechanics of how that works? Because you always hear people say the motor runs in reverse, but that doesn't really explain how it stops a 4,000-pound car.
Yeah, saying the motor runs in reverse is a bit of an oversimplification.
Okay, so what's really happened?
When you lift your foot off the accelerator, the car stops sending electricity to the motor. Instead, the forward momentum of the car keeps the wheels turning, and the wheels physically turn the motor.
Oh, I see.
This essentially turns the electric motor into a generator. As it generates electricity to feed back into the battery, it creates a massive amount of magnetic resistance.
Fascinating.
Right. That magnetic drag is what physically slows the vehicle down, capturing the kinetic energy instead of just, wasting it as heat on a brake pad.
Which sounds like a miracle technology because you rarely ever use your physical brake pads.
It is brilliant, yes.
But Car and Driver points out a massive downside to this. The lack of use actually causes the traditional mechanical brakes to rust and seize up.
Right. The mechanical brakes are still there for emergency stops, but they sit idle for like 95% of your driving.
Yeah, because the magnets are doing all the work.
Exactly. So
Hmm.
in areas that use salt on the roads during winter, those idle metal components just get coated in corrosive moisture. Without the regular heat and friction of daily braking to burn off that moisture and rust, the calipers simply seize.
And get this, Tesla literally requires a $100 service every 12 months or 12,500 miles just to take the brakes apart and lubricate the calipers in snowy or salty areas.
Wow.
You are paying a mechanic $100 to maintain brakes you barely even use.
It really represents a fundamental shift in vehicle ownership. An electric vehicle shifts the maintenance burden from the engine to the edges.
The edges.
Yeah, the center of the car, the battery, and the motors is virtually sealed. But the edges, the tires, the brakes, the suspension, holding up all that weight, that is where your attention and your money actually have to go.
That is a perfect way to put it. Speaking of where your money goes, we need to talk about the battery itself. The National Renewable Energy Lab predicts these batteries will last 12 to 15 years in moderate climates, but only 8 to 12 years in extreme ones.
Which isn't terribly long in car years.
No, not at all. And the sources point out that one of the biggest factors in degrading them prematurely is fast charging. We hear terms like level 1, level 2, and level 3 charging. How does fast charging actually damage the battery chemistry?
It basically comes down to the difference between alternating current and direct current. Level 1 and level 2 chargers, the kind you usually use at home, supply AC power from the grid.
Okay, standard house power.
Right. The car has an onboard converter that slowly changes that AC power into DC power, trickling it safely into the battery.
Love it.
Level 3 fast chargers, however, are massive commercial stations that bypass the car's converter entirely. They blast high amperage direct current straight into the battery pad.
That sounds aggressive.
It is. Shoving that much energy directly into the cells in such a short amount of time generates an immense amount of heat. And that physically stresses and degrades the delicate lithium-ion cell structures over time.
Oof. Not only does it stress the battery, but it also really stresses your wallet. Car and Driver notes that commercial fast charging costs 3 to 4 times more than charging at home.
Wow. Yeah.
They found it can cost up to $100 to fully charge a Hummer EV from empty at a fast charger.
$100.
$100. If you were listening to this thinking, wait, I thought the whole point of an EV was to avoid the $100 trip to the gas station. Well, there it is.
Yeah, that's steep.
If fast charging degrades the battery over time and can cost a fortune, isn't the convenience of rapid charging actually a financial trap?
Honestly,
Yeah.
if you rely on level 3 charging as your primary method of fueling, it absolutely is a trap. It negates almost all the economic benefits of going electric.
So what's the alternative?
Well, that infrastructure is designed for road trips and necessities, not for daily use. The golden rule for EV care, to protect both the lifespan of the battery and your bank account, is home charging.
Right.
And specifically, you want to manage the state of charge. You should never charge to 100% for daily driving and never let it deplete to 0. The daily limit should be set around 85 or 90%.
Okay, so if driving the car daily wears down the tires, rusts the brakes, and degrades the battery. You might logically think the easiest way to preserve the vehicle is just to park it in a garage and give it a rest for a few months.
You'd think so, wouldn't you?
But the expert guide on storage makes it remarkably clear. Leaving an EV alone for months is actually when it requires the most meticulous, psychological level of care.
Yeah, you cannot just toss a tarp over it and walk away like you might with an old gas-guzzling classic car.
Definitely not. The storage sweet spot for the battery is exactly 50 to 60% state of charge. The sources say if you leave it at 100%, it causes high voltage stress and chemical aging. If you leave it at 0%, it causes deep discharge damage that can permanently kill the battery.
Which is a nightmare.
Why is 50% the magic number, though?
Think of the battery chemistry like a physical rubber band. If you store a rubber band stretched as far as it can go that is the equivalent of a 100% charge over time, it loses its elasticity and degrades.
Okay, I can picture that.
And if you store it completely crumpled up at 0%, the material can become brittle and crack. 50% is its natural, unstressed resting state. The positive and negative ions inside the lithium cells are perfectly balanced right there.
That makes total sense.
Yep.
Getting the
Yeah.
car to exactly 50% is one thing, but then you have to fight this issue called vampire drain.
Ah, yes. Vampire drain.
The car is essentially a giant computer that never fully sleeps. The sources explain you have to aggressively turn off features like Sentry Mode and cabin overheat protection. What are these computers actually doing while the car is parked in a dark garage that drains so much power?
Well, modern electric vehicles are incredibly active when they're parked. They are constantly pinging cellular networks to check for software updates, running background diagnostics, and most importantly, running thermal management systems to ensure the battery doesn't get too hot or too cold while just sitting there,
Even when it's off.
even when it's off. Every time the car wakes up to perform one of these tasks, it draws power from the main high-voltage battery. Over weeks or months, that vampire drain can pull a battery down from a safe 50% to dangerously low levels.
Jeez. The storage guide even says you have to keep your key fob far away from the garage so the car doesn't constantly sense the proximity key and wake up the screens to greet you.
It's like a needy pet.
It really is. If you are storing the car for 3 months or more, they recommend keeping it plugged into the wall. But going into the software and telling the car to only charge if it drops below 40% and to stop charging the moment it hits 50%, you are essentially putting the vehicle on a highly controlled, automated life support drip.
And that life support drip is crucial because if the main battery dies, you face a cascading failure.
Which brings me to the most baffling part of the storage guide. Every EV still has a tiny, normal 12-volt car battery sitting under the hood, right alongside the massive high-voltage pack that drives the wheels.
Yep, just like a normal gas car.
Right. Why does a car with a giant battery spanning the entire floorboard even need a tiny traditional battery?
It is actually a vital safety mechanism. When you turn off an electric vehicle, the car physically severs the connection to the massive high-voltage battery using heavy-duty contactors.
Oh, to keep it safe.
Exactly. This ensures the car isn't a live high-voltage hazard while parked or in an accident. The little 12-volt battery is the only thing left running. It powers the door locks, the alarm, the computer screens, and crucially, it powers the computer that tells those contactors to close and reconnect the main high-voltage pack when you actually want to drive.
Wow. So what does this all mean? The 12-volt battery acts like the brainstem of a giant creature.
That's a great way to think about it.
It means you can have a massive, perfectly preserved 60% high-voltage battery, but if you do not connect a maintainer to the little 12-volt battery and it dies while in storage, the car's computer cannot even turn on to engage the main battery. It's like owning an impenetrable high-tech fortress, but losing the tiny, flimsy metal key to the front door. The entire system is just bricked.
It is an incredibly frustrating mistake people make all the time. The main battery is perfectly fine, but because the 12-volt system died, the car has to be physically towed to a service center just to be woken up.
Unbelievable. And the physical preparation for storage is just as intense. The guide says you have to inflate the tires to the sidewall max pressure, not the normal pressure listed on the driver's door jamb.
Right, the max pressure.
You have to overinflate them so the immense weight of the EV doesn't cause permanent flat spots in the rubber while it sits in one position for months.
Correct. You are trying to brace the tires against the continuous downward force of all those battery packs.
You were also warned not to use the parking brake because, as we learned, idle brakes rust and seize up, Mm. Instead, you have to physically block the wheels with chocks.
Old school.
Very old school. You even have to put cardboard under the windshield wipers so the rubber blades don't chemically bond to the glass over time.
And waking the car up from this state requires a very deliberate reactivation process. You don't just jump in and peel out of the garage.
What do you have to do?
You have to perform a visual inspection, check the undercarriage for any coolant leaks from the thermal management system, and let the computer systems fully recalibrate when you power it on. Then, you have to drive slowly and gently apply the mechanical brakes several times to scrape off all that surface rust that accumulated on the rotors while it was sitting.
Man. We started out looking for the hidden life of your electric vehicle, and it turns out it requires a fascinating level of involvement. From preheating the battery on grid power, to bracing for rapid tire wear, to putting it on life support during storage, owning one of these vehicles demands a completely new mindset.
It really does. And if we look down the road, this raises a profound question about the future. We established that EV batteries are rated to last roughly 12 to 15 years. We have just spent this entire deep dive detailing the intense micromanagement required to get them to that age, monitoring thermal loads, avoiding fast chargers, and managing exact storage capacities.
Yeah, it's a lot of work.
It is. So what does the future of the used car market look like? In a decade, are we going to see a massive wave of perfectly good, rust-free car bodies tethered to heavily degraded out-of-warranty batteries simply because the previous owners didn't micromanage the chemistry?
That's a scary thought.
Will this force the creation of massive, entirely new battery refurbishing industries just to keep these rolling computers out of the scrapyard? We are stepping into an era where the lifespan of a vehicle is entirely dictated by the chemistry of its battery rather than the physical durability of its chassis.
That reframes the entire concept of vehicle ownership. The car itself almost becomes secondary to the power source.
Absolutely.
Well, thank you so much for taking the time to explore this with us today. We really appreciate you joining the conversation and going beyond at the surface level marketing. Whether you are heading out into the freezing cold for your morning commute or painstakingly parking your car for the winter season, we hope you feel empowered with the actual mechanics of how to protect your electric steed. Until next time, stay curious.